Tonight, we're going to confront something you think you already understand, but almost certainly do not. The distance between the planets. You have seen the diagram. 8 worlds lined up neatly beside the sun, almost touching, like beads on a string. That picture is one of the most dangerous lies in science education, because it makes the solar system feel like a road. Like you could simply hop from one planet to the next if you had a fast enough ship. The truth is that the gaps between those planets are not just large, they are alive. They change every day. They demand curved paths, brutal timing, and years of travel. And the farther out you go, are you ready to see what is actually between the planets? Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. Are you comfortable? Let's begin. You have seen the solar system 1,000 times. It was pinned to the wall of your classroom. It was printed in the opening pages of your science textbook. It was projected onto a screen during a lecture you half remember from middle school. And every single time you saw it, the picture looked roughly the same. The sun on the left, usually bright yellow, and then a neat row of planets marching off to the right. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. Each one a visible disk. Clearly colored, evenly spaced, almost close enough to touch the one next to it. Some curved the line into a gentle arc. Some added rings around Saturn and a tiny red spot on Jupiter. Some threw in Pluto at the far end with an apologetic asterisk. But they all shared the same basic structure. A tidy row of worlds arranged beside their star, like fruit on a shelf. That picture is not just simplified. It is actively wrong in ways that shape how nearly every person on Earth thinks about the solar system. It makes the planets look close together. It makes the spaces between them look manageable. It makes the whole system feel like a road with stops along the way, as if you could visit each planet in turn the way you might drive through towns on a highway. And that intuition, that quiet assumption that the planets are nearby neighbors separated by modest gaps, is one of the most misleading ideas in all of popular science. The reason every diagram looks like this is not laziness. It is necessity. The actual distances between the planets are so absurdly large relative to the sizes of the planets themselves that no honest picture can show both at the same scale. If you try to draw the solar system to scale on a sheet of paper, with the planets drawn at their correct sizes relative to the gaps between them, every planet would be invisible. Not small, invisible. A dot too small to see with the naked eye, surrounded by emptiness stretching across meters of blank paper before the next invisible dot appeared. That is what the solar system actually looks like. And no classroom poster, no textbook diagram, no documentary animation can show you that without making the planets disappear entirely. So every diagram you have ever seen makes a choice. It keeps the planets visible by inflating their sizes enormously while compressing the distances between them by factors of tens of thousands. The result is something useful as a label chart. You can see the order, you can see the colors, you can see which ones have rings. But as a picture of where things actually are in space, relative to one another, it is about as accurate as drawing a map of the United States, where New York and Los Angeles are 2 inches apart. Let's talk about what the real distances look like, because until you see the actual numbers, the diagram's distortion does not fully register. Astronomers measure distances within the solar system using a unit called The astronomical unit. One astronomical unit is the average distance from the Earth to the Sun, approximately 150 million kilometers. That is roughly 93 million miles. Light covers this distance in about 8 minutes and 20 seconds. It is a useful measuring stick because it gives you an intuitive anchor point. Earth sits at 1 astronomical unit from the Sun. Everything else is measured relative to that. Mercury, the innermost planet, orbits at about 0.39 astronomical units from the Sun. Venus is at about 0.72. Earth, by definition, is at 1. Mars is at about 1.52. These 4 planets, the rocky inner worlds, are all clustered within a surprisingly small region. From Mercury to Mars, the entire span of the inner solar system covers only about 1.13 astronomical units. In terms of raw distance, that is roughly 170 million kilometers from the innermost planet's orbit to the outermost inner planet's orbit. That sounds enormous by human standards, and it is, but by solar system standards, it is a tiny neighborhood. Now look at what happens as you move outward. Jupiter orbits at approximately 5.2 astronomical units from the Sun. That is more than 3 times farther from the Sun than Mars is. The gap between Mars and Jupiter alone, roughly 3.7 astronomical units, is wider than the entire span of the inner solar system. Saturn sits at approximately 9.58 astronomical units. Uranus is at approximately 19.14. Neptune is at roughly 30.2 astronomical units. Read those numbers again carefully. Mercury to Mars covers about 1.13 astronomical units. Mars to Jupiter covers about 3.7. Jupiter to Saturn covers about 4.4. Saturn to Uranus covers about 9.6. Uranus to Neptune covers about 11 astronomical units. The gaps are not just growing as you move outward, they are accelerating. Each step between planets is larger than the last. The distance from Saturn to Uranus alone is roughly 8.5 times the entire width of the inner solar system. The distance from Uranus to Neptune is almost 10 times that width. The outer solar system is not just bigger than the inner one, it is a different category of big. And no classroom diagram communicates this because compressing those distances is the only way to fit the whole system onto a single page. Here is one way to feel this. If you shrank the Sun down to the size of a front door, about 1 meter across, Earth would be a small bead roughly the diameter of a pencil eraser, sitting about 107 meters away. That is longer than a football field. Mercury would be a grain of sand about 42 meters from the door. Mars would be a slightly smaller bead, 163 meters out. You would already need a city block to contain just the inner solar system. Jupiter, at this scale, would be a ball roughly the size of a grapefruit, sitting 556 meters away from that front door. That is over 5 city blocks of empty space with almost nothing in between. Saturn would be a ball about the size of an orange at just over a kilometer. Uranus would be a walnut roughly 2 kilometers away. And Neptune would be a slightly smaller walnut at 3.2 kilometers from the front door that represents the Sun. 3.2 kilometers. You would need to walk for nearly 40 minutes at a brisk pace to travel from the Sun to Neptune in this model. And along the way, you would pass exactly 8 objects, each one too small to notice unless you knew exactly where to look. Everything else would be empty air. That is what the solar system actually looks like when you scale the distances and the sizes together. Emptiness with tiny specks scattered through it at widening intervals. The diagram on the classroom wall shows you none of this, but the diagram does something even more misleading than compressing distances. It freezes the planets in place. In every textbook image, every poster, every animation that lines the planets up in a row, the planets are standing still. They are fixed points at fixed distances, as if they were pinned to a board. Mercury is always in the same spot. Mars is always in the same spot. Jupiter is always in the same spot. The diagram implies that the distance between any two planets is a single number that you could look up and rely on. The way you might look up the distance between two cities. That is not how the solar system works. Not even close. Every planet in the solar system is in constant motion, orbiting the sun at its own speed, on its own elliptical path. Mercury screams around the sun in just 88 Earth days, traveling at an average orbital velocity of about 47 kilometers per second. Venus takes about 225 days. Earth takes 365 and a quarter days. Mars takes about 687 days, just under 2 Earth years. Jupiter takes nearly 12 Earth years to complete a single orbit. Saturn takes about 29.5 years. Uranus takes 84 years. Neptune takes roughly 165 years to go around the Sun once. Because these planets orbit at different speeds, their positions relative to each other are constantly changing. Two planets are sometimes on the same side of the Sun, relatively close together. Other times, they are on opposite sides, with the entire diameter of their orbits plus the Sun's distance separating them. And most of the time, they are somewhere in between, neither at their closest nor at their farthest, but at some intermediate distance that shifts every single day. Take Earth and Mars as the most familiar example. At their closest approach, called opposition, when Earth passes directly between Mars and the Sun, the two planets can be as near as approximately 55 million kilometers. That is close by planetary standards, roughly 0.37 astronomical units. But opposition does not happen on a fixed schedule. Because both orbits are elliptical, the closeness of each opposition varies. Some oppositions bring Mars within about 55 million kilometers. Others bring it no closer than about 100 million kilometers. The difference depends on where each planet happens to be in the slightly elongated shape of its own orbit at the moment of closest approach. And at their farthest, when Earth and Mars are on opposite sides of the Sun, the distance between them can stretch to approximately 401 million kilometers. That is more than 7 times the closest approach distance. 7 times. The distance between Earth and Mars is not a number. It is a range, and that range swings from 55 million to 400 million kilometers, depending on a geometry that never repeats exactly the same way, twice. This variability is not unique to Mars. Every pair of planets in the solar system experiences the same constant shifting. The distance between Earth and Jupiter varies from roughly 588 million kilometers at closest approach to about 968 million kilometers at their farthest. The distance between Earth and Saturn ranges from roughly 1.2 billion kilometers to about 1.67 billion kilometers. For the outer planets, these ranges become truly staggering. Earth and Neptune can be separated by as little as about 4.3 billion kilometers, or as much as about 4.7 billion kilometers. So when someone says the distance between two planets is a certain number, what they almost always mean is the average distance between their orbits, or sometimes the distance at closest approach. Neither of those numbers tells you where the planets actually are right now, today, relative to each other. The real distance is a moving target, changing every hour of every day as both worlds swing around the sun at different speeds. This has enormous consequences for space travel, because it means you cannot simply decide to fly to another planet whenever you feel like it. You have to wait for the geometry to be right. If Mars is on the far side of the sun when you want to launch, the journey is not just longer. It is essentially impossible with current or near-future propulsion, because you would be fighting the entire geometry of the solar system instead of working with it. The practical result is that missions to Mars can only launch during specific windows, brief periods when the two planets are positioned in a way that makes a transfer efficient. Those windows come roughly every 26 months. Miss one, and you wait more than 2 years for the next opportunity. For the outer planets, the windows are more frequent because their orbits are so much slower relative to Earth's. But the travel times are so much longer that the window matters in a different way. It determines not just when you launch, but what trajectory you take, how much fuel you need, and how many years the journey will last. And here is the part that most people never think about. You cannot fly to another planet in a straight line. This is the deepest misconception that the classroom diagram creates. When you see 8 planets lined up in a row, your brain naturally imagines travel as a straight shot from one world to the next. Point your rocket at Mars, fire the engines, coast across the gap, arrive. That is how it works in most science fiction. That is how it feels like it should work based on everyday experience with cars, planes, and boats, but orbital mechanics does not allow it. Every object in the solar system is in orbit around the sun. The Earth is not standing still. It is moving at approximately 30 kilometers per second along its orbital path. Any spacecraft that launches from Earth inherits that velocity. It is already moving at 30 kilometers per second in the direction of Earth's orbit. To reach another planet, the spacecraft does not simply point itself at the target and fly across. It has to change its orbit around the sun so that the new orbit intersects with the target planet's orbit at precisely the right place and time. The most fuel-efficient way to do this was described by a German engineer named Walter Hohmann in 1925. The idea is elegant in concept and unforgiving in practice. Instead of flying directly toward the target planet, you fire your engines at exactly the right moment to enter an elliptical orbit, whose closest point to the sun touches Earth's orbit, and whose farthest point touches the target planet's orbit. You coast along this long curving arc for months or years, and if everything was timed correctly, the target planet arrives at the far end of that arc at exactly the same moment you do. This is called a Hohmann transfer orbit, and it is the foundation of almost every interplanetary mission ever flown. But notice what it requires. The spacecraft is not traveling toward the planet. It is traveling along a curved path around the sun, and the planet happens to be at the endpoint of that curve when the spacecraft arrives. If the timing is off by even a few days, the spacecraft arrives at the right point in space, but the planet is not there. It is somewhere else along its orbit, millions of kilometers away, and there is no way to correct for that once you are coasting along the transfer arc. This means the actual distance a spacecraft travels to reach another planet is always much greater than the straight line distance between the two worlds. A Hohmann transfer from Earth to Mars covers a path of roughly 500 million kilometers along the elliptical arc, even though the straight line distance at departure might be only 70 or 80 million kilometers. The spacecraft is not crossing a gap. It is following a curve that swings it outward from the Sun, and that curve is dictated by the laws of gravity, not by human preference. For the outer planets, these curved paths become enormously long. A Hohmann transfer to Jupiter traces an arc of roughly 1.3 billion kilometers. To Saturn, roughly 2 billion kilometers. To Uranus, roughly 3.5 billion kilometers. To Neptune, roughly 5.2 billion kilometers. And in practice, real missions travel far longer paths than even these arcs, because they rely on gravity assists that loop the spacecraft through the inner solar system multiple times before heading outward. A spacecraft bound for Jupiter might fly past Venus, return to Earth, and swing outward again, doubling or tripling the Hohmann arc distance before it ever leaves the inner solar system for good. The actual distance a spacecraft covers to reach an outer planet is always far greater than the straight line gap between the two worlds. And here is what makes all of this worse. You cannot speed up the journey by simply burning more fuel at the beginning. You can shorten a Hohmann transfer by using a faster, less fuel-efficient trajectory, but that requires exponentially more propellant. The relationship between speed and fuel in rocketry is governed by the Tsiolkovsky rocket equation, and it is merciless. Every additional kilometer per second of velocity you want at departure demands a disproportionately larger amount of fuel. Doubling your speed does not require twice the fuel. It requires many times more, because you have to accelerate not just the spacecraft, but all the extra fuel you are carrying to provide that extra acceleration. The mathematics create a wall. Beyond a certain speed, the fuel required to go faster exceeds any reasonable mass budget. You simply cannot carry enough. This is why interplanetary travel is not just a matter of distance. It is a matter of distance combined with motion, timing, trajectory, and fuel. The planets are not stations on a rail line. They are moving targets on elliptical tracks, each traveling at its own speed, each separated from the others by gaps that change every day. Reaching any one of them requires launching at precisely the right moment, following a long curved path around the Sun, arriving at precisely the right point months or years later, and doing all of it with a finite supply of fuel that constrains every decision. The classroom diagram shows you none of this complexity. It shows 8 worlds in a row and lets you imagine that the journey between them is as simple as the picture. It teaches you the names and the order and the colors, and it leaves you with an intuition about planetary travel that is almost entirely wrong. What follows in this story is what happens when that wrong intuition meets reality. We are going to start with Mars, the planet that sits closest to us in the outward direction, the one that every space agency and every private company talks about reaching within the next few decades. And we are going to see that even this nearest, most familiar target, the planet we have mapped in extraordinary detail with rovers and orbiters, is already hard enough to make mission planners lose sleep. Because if the diagram lies about how far apart the planets are, it lies even more about how difficult the spaces between them truly are. And every step outward from Mars only makes it worse. Mars is the planet everyone talks about. It is the planet on the mission patches, in the press conferences, in the ambitious timelines pinned to whiteboards at space agencies around the world. When people say humanity will become an interplanetary species, they almost always mean Mars first. And there is good reason for that. Mars is, by almost every relevant metric, the easiest interplanetary destination we have. It is the closest planet in the outward direction from Earth. It has a solid surface you can land on. It has a thin atmosphere that can help with braking during entry. Its day is almost the same length as Earth's, roughly 24 hours and 37 minutes. It has water ice locked in its polar caps and buried beneath its surface. It has been studied more extensively than any other planet beyond Earth, mapped down to the meter scale by orbiters, sampled by landers, driven across by rovers. If any planet should feel reachable, it is Mars. And yet, reaching Mars is one of the hardest things humanity has ever attempted. The missions that have made it there represent decades of engineering at the absolute edge of what is possible. The missions that failed, and there have been many, illustrate how unforgiving the journey is. Mars is the easiest destination, and it is still brutally punishingly difficult. Understanding why is the first step in understanding why every planet beyond Mars becomes worse. Start with timing. As we covered, the distance between Earth and Mars is not fixed. It swings between roughly 55 million kilometers at the closest and roughly 400 million kilometers at the farthest. But even at its closest, you cannot simply launch a rocket toward Mars and fly across. You have to enter a Hohmann transfer orbit, that long elliptical arc around the Sun, whose far end meets Mars at exactly the right moment. And that arc takes time. A minimum energy Hohmann transfer from Earth to Mars takes approximately 8 to 9 months, depending on the exact geometry of that particular launch opportunity. During those months, the spacecraft is not flying toward Mars in the way a plane flies toward a city. It is coasting along a curved path that swings outward from the Sun, carried by the momentum of its departure burn, plus the gravitational geometry of the Sun itself. The spacecraft crosses a distance of roughly 500 million kilometers along this arc, even though the straight line distance to Mars at the moment of departure might be a fraction of that. And here is what makes the timing especially cruel. You cannot launch whenever you want. The Hohmann transfer works only when Earth and Mars are in a specific geometric relationship. Earth needs to be behind Mars in its orbit by a precise angle, so that by the time the spacecraft completes its long curved journey, Mars has moved forward along its own orbit to meet it. This alignment occurs roughly every 26 months. That gap between windows is called the synodic period, and it is the heartbeat of every Mars mission ever planned. If you miss a launch window, you do not wait a week. You do not wait a month. You wait 26 months for the next opportunity. Over 2 years of waiting because the planets have moved out of alignment, and no amount of engineering can change the orbital geometry. This is not a constraint that better technology will fix. It is a consequence of how orbits work. As long as Earth and Mars circle the Sun at different speeds, this 26-month cycle is permanent. Every Mars mission in history has been shaped by this constraint. The twin Viking landers launched in August and September of 1975 and arrived at Mars in June and August of 1976. The Curiosity rover launched in November of 2011 and landed in August of 2012. The Perseverance rover launched in July of 2020 and landed in February of 2021. In each case, the launch date was dictated not by when the engineers were ready, but by when the planets were ready. If a technical problem delayed the spacecraft past the end of the launch window, the entire mission would slip by over 2 years. This has happened. Missions have been delayed by full synodic cycles because they were not ready in time, sitting fully built in clean rooms, waiting for the solar system to rotate into position again. Now, consider what happens during the transit. For those 8 or 9 months of coasting, the spacecraft is alone. It left Earth behind. Mars is ahead, but not visibly. For most of the journey, Mars is just another dot among millions in the sky. The spacecraft cannot see its destination getting closer in any meaningful way. It is simply following its orbital arc, trusting the mathematics that say Mars will be there at the other end. During this time, communication with Earth is possible, but it is not like any communication you are used to. Radio signals travel at the speed of light, roughly 300,000 kilometers per second. At the start of the journey, when the spacecraft is still relatively close to Earth, the delay is modest, a few minutes each way. But as the spacecraft moves along its transfer arc and the distance to Earth changes, the delay fluctuates. Depending on where Earth and Mars are in their respective orbits, the one-way signal travel time between the two planets ranges from roughly 3 minutes at the very closest to over 22 minutes at the very farthest. Think about what a 22-minute one-way delay means in practice. You send a command to the spacecraft. 22 minutes later, the spacecraft receives it. If something goes wrong and the spacecraft sends an alert back to Earth, another 22 minutes pass before you receive it. By the time you know there is a problem, the problem has been happening for 22 minutes. By the time your response reaches the spacecraft, 44 minutes have passed since the problem began. 44 minutes where a failing system has been failing, an error has been compounding, a trajectory has been drifting, with no human intervention possible. This is why Mars rovers drive themselves. When Perseverance navigates across the Martian surface, it uses onboard cameras and autonomous software to identify obstacles, plot paths, and make decisions in real time. Ground controllers send high-level instructions, drive to that rock formation, analyze that soil patch, but moment-to-moment navigation is handled by the rover itself. By the time a human controller saw a hazard, decided on a response, and transmitted the corrective command, the rover would have already driven into it or past it. For robotic missions, this is manageable. Rovers are patient. They can stop and wait for instructions. They do not panic. They do not bleed. They do not run out of air. But for a human crew in transit to Mars, the communication delay is not just an inconvenience, it is a fundamental alteration of the relationship between the crew and everyone they have ever known. During the early days of the journey, conversations with Earth are almost normal. A few minutes of lag, annoying but workable, like a bad video call. But as the weeks pass and the distance grows, the lag stretches. 5 minutes, 10 minutes, 15. Eventually a round-trip exchange takes the better part of an hour. That means no real-time conversations, no immediate advice from mission control during a medical emergency, no quick call home to hear a family member's voice and get a response before the emotion fades. Every interaction becomes an exchange of recorded messages, sent and received with gaps long enough to drain the spontaneity out of any human connection. You speak into the void and wait. The answer comes later, from a world that feels increasingly like a memory. And then there is the matter of rescue. There is no rescue on a Mars mission. This is stated plainly in every serious mission study, but it is worth pausing on because it represents a psychological reality that has no precedent in human spaceflight. Every astronaut who has ever flown in orbit around Earth, from the earliest Mercury flights to the International Space Station, has operated within a few hundred kilometers of the surface. If something goes catastrophically wrong, there are contingency plans, emergency re-entry procedures, escape capsules, the possibility, however slim, that help could arrive. On a Mars transit, none of that exists. Once the spacecraft leaves Earth orbit and enters its transfer arc, it is on its own. If a critical system fails 3 months into a 9-month journey, Earth cannot send a repair crew. There is no second spacecraft waiting on standby. There is no way to turn around because the spacecraft is coasting on an orbital path that does not allow for reversal without an amount of fuel it does not carry. The crew would have to fix the problem with whatever tools, spare parts, and expertise they brought with them. If they cannot fix it, the consequences are final. This is not theoretical risk assessment. This is the operational reality of every Mars mission plan that has ever been seriously studied by NASA, the European Space Agency, or any private organization. The crew must be prepared to handle every conceivable emergency, medical, mechanical, structural, without any possibility of outside help, for a minimum of roughly 2.5 to 3 years. That is the total mission duration for a typical conjunction-class Mars mission. 9 months of transit to Mars, a surface stay of roughly 15 to 18 months while waiting for the planets to realign for the return trip, and another 9 months of transit back to Earth. 2.5 to 3 years. Completely self-sufficient. No resupply, no rescue. Let's talk about what the trajectory actually looks like, because visualizing it helps you understand why this is not just far, but geometrically strange. At the moment of departure, the spacecraft fires its engines to increase its orbital velocity around the Sun. This pushes it onto a wider orbit, one that gradually swings outward from Earth's orbital distance toward Mars's orbital distance. The spacecraft is not traveling away from the Sun in a straight line. It is spiraling outward along a gentle curve, still orbiting the Sun the entire time, just on a wider path than Earth follows. Meanwhile, Earth continues on its own orbit behind the spacecraft, moving faster because it is closer to the Sun. And Mars, up ahead, is moving along its own orbit at roughly 24 kilometers per second. Slower than Earth's roughly 30 kilometers per second, but still covering vast distances every day. The spacecraft, Mars and Earth, are all moving simultaneously. The entire system is in motion. The transfer is not a crossing from one fixed point to another. It is a choreographed convergence of 3 moving objects: the spacecraft, the departure planet, and the arrival planet, all obeying the gravitational laws of the Sun. When the spacecraft finally arrives at Mars's orbital distance, roughly 8 or 9 months later, it has to enter orbit or land. But it arrives moving at a different velocity than Mars. The spacecraft is on a transfer orbit with a specific speed at that distance from the Sun. Mars is on its own orbit with a different speed. The difference between these velocities is called the arrival delta V, and the spacecraft has to burn fuel to match Mars's speed. If it does not, it simply sails past, continuing on its elliptical orbit, back toward the inner solar system. There is no stopping without fuel. There is no coasting into orbit without a deliberate, precisely timed engine burn. This arrival burn is one of the most critical moments of the entire mission. If the engine fails to fire, the spacecraft overshoots Mars and enters an orbit around the Sun that may never bring it back to any useful destination. If the burn is too short, the spacecraft enters a wrong orbit. If it is too long, fuel is wasted that may be needed later. Every parameter has to be correct. And because of the communication delay, the burn typically has to be executed autonomously by onboard computers, with ground controllers watching helplessly from millions of kilometers away, learning the outcome minutes after it has already happened. The history of Mars exploration is littered with missions that failed at exactly this point. Mars has earned a grim reputation among mission planners. Of all the missions ever sent to Mars by every space agency on Earth, roughly half have failed. Some failed during launch. Some failed during transit. Some failed during the entry, descent, and landing sequence. The period mission controllers call the 7 minutes of terror, because the spacecraft must decelerate from roughly 20,000 kilometers per hour to zero in about 7 minutes, entirely autonomously, with the communication delay making real-time intervention impossible. The entry sequence alone illustrates the brutality of Mars operations. A spacecraft approaching Mars hits the top of the Martian atmosphere at roughly 5.7 kilometers per second. That is about 20,500 kilometers per hour. The atmosphere is thin, only about 1% the density of Earth's atmosphere at sea level, which means it provides some braking but not enough to slow the spacecraft to a safe landing speed on its own. So the spacecraft must use a combination of atmospheric friction, parachutes, and powered descent, firing retro rockets in the final seconds to bring itself from hypersonic speed to a gentle touchdown. All of this happens in sequence, each phase, depending on the previous one, executing correctly. If the heat shield fails during atmospheric entry, the spacecraft burns up. If the parachute does not deploy, the spacecraft hits the surface at hundreds of kilometers per hour. If the retro rockets misfire, the spacecraft crashes or tips over. Each transition is a single point of failure with no backup and no human override. And the entire sequence is over before Earth even knows it has begun, because the light travel time from Mars to Earth is longer than the 7 minutes the landing takes. When Perseverance landed in Jezero Crater in February of 2021, mission controllers at the Jet Propulsion Laboratory watched telemetry that was already 11 minutes old. Every signal they received, every confirmation of parachute deployment, every radar altimeter reading had already happened 11 minutes earlier. The rover was either safely on the surface or destroyed, and the people responsible for its fate had no power to change the outcome. They could only sit and wait and listen to signals from the past. This is Mars, the easy one, the close one, the planet we know better than any other world beyond Earth. Now, layer on top of all this the fact that a human mission to Mars is not a robotic lander that can be replaced if it fails. It is people. People sealed inside a spacecraft for 9 months, subjected to cosmic radiation at rates that exceed what any astronaut has experienced on the International Space Station. The station orbits within Earth's magnetic field, which deflects most charged particles. A Mars transit spacecraft would be outside that protection, exposed to galactic cosmic rays and the occasional solar particle event. Streams of high-energy protons blasted out by solar flares that can deliver dangerous radiation doses within hours. Shielding helps, but no practical amount of shielding stops everything. The crew accumulates radiation exposure throughout the journey, increasing their lifetime cancer risk with every passing week. They would also experience the physiological effects of weightlessness, or of whatever partial gravity the spacecraft provides through rotation. Bone density loss, muscle atrophy, fluid redistribution, vision changes caused by increased intracranial pressure. These are not hypothetical concerns. They are documented effects observed in every long-duration astronaut aboard the International Space Station. Scott Kelly, who spent 340 days aboard the station, returned to Earth with measurable changes in gene expression, immune function, and vision. A Mars transit crew would spend roughly the same amount of time in similar conditions, but without the option of an emergency return to Earth if their health deteriorates. And after 9 months of transit, the crew does not get to come home. They arrive at Mars and face another set of challenges. Landing a crew vehicle on Mars is something humanity has never done. The largest object we have successfully landed on Mars is the Perseverance rover, which weighed roughly 1,025 kilograms. A crewed lander with life support, supplies, surface habitats, and a return vehicle would weigh tens of thousands of kilograms. Scaling up the landing technology from a 1-ton rover to a multi-ton crewed vehicle is an unsolved engineering problem. The thin Martian atmosphere does not provide enough drag to slow a heavy vehicle sufficiently. And the parachute and retro rocket systems that work for small payloads do not scale linearly. Once on the surface, the crew must survive in an environment that is actively hostile to human life. The Martian atmosphere is 95% carbon dioxide, with almost no oxygen. Surface temperatures average roughly minus 60 degrees Celsius and can plunge below minus 100 degrees Celsius at the poles. The atmospheric pressure is less than 1% of Earth's. So low that exposed liquid water boils immediately. Radiation on the surface is significantly higher than on Earth because Mars has no global magnetic field and only a wisp of atmosphere to block cosmic rays. The crew would live inside pressurized habitats, venturing outside only in spacesuits, dependent entirely on technology they brought with them for every breath of air, every sip of water, and every calorie of food. And they would stay for over a year. Not because they want to, but because they have to. The same orbital geometry that dictates launch windows also dictates when you can leave Mars and return to Earth. After arriving, the crew must wait approximately 15 to 18 months for Earth and Mars to swing back into the correct alignment for a return transfer. During that entire wait, they're on Mars. If a critical habitat system fails during month 3 of the surface stay, Earth cannot send a replacement part. The next cargo delivery opportunity is more than a year away, assuming one was even planned. The crew must be entirely self-sufficient for the duration of the surface stay, repairing systems with onboard spares, recycling air and water, growing supplemental food if possible, managing medical emergencies with whatever pharmaceutical and surgical supplies they brought. What does that actually look like day after day for 15 months? The crew lives inside pressurized habitats roughly the size of a modest apartment, shared among 4 to 6 people. Every cubic meter of that space is allocated. Sleeping quarters. A galley where meals are prepared from a combination of pre-packaged food and whatever can be grown under artificial light in a small hydroponic bay. A workstation for monitoring habitat systems. A medical bay that doubles as a storage closet. An airlock for surface excursions. There is no living room. There is no yard. No room you can walk into just to be somewhere different. The habitat is the entire world, and it has the same dimensions on day 450 that it had on day 1. Water is recycled. Every drop of moisture, from breath condensation to hygiene runoff to urine, is captured, filtered, and returned to the supply. The International Space Station already does this, recovering roughly 93% of water through a system that astronauts have described as functional but psychologically difficult. Intellectually, that the water is clean. The filtration process is rigorous, but you also know where the water was an hour ago. On Mars, with no resupply, the recycling efficiency has to be pushed even higher, closer to 98 or 99%. Every percentage point of loss accumulates over 15 months. A 2% loss rate across 450 days means the crew slowly runs through its reserves. If the recycling system degrades, if a filter clogs or a membrane develops a microfracture, the water budget tightens. There is no rain on Mars. There is no river. There is only what you brought and what you can reclaim. Air follows a similar logic. The habitat's atmosphere is maintained by systems that scrub carbon dioxide and replenish oxygen, either through chemical processes or through electrolysis of water. These systems run continuously, every hour of every day, for over a year. If the carbon dioxide scrubber fails at 2 a.m. on a Tuesday during month 11 of the surface day, the crew has to fix it. Not tomorrow. Not after a call to mission control and a 4-hour wait for a response. Now. Because carbon dioxide builds up quickly in a sealed environment, and the symptoms of elevated carbon dioxide, headaches, confusion, impaired judgment, are exactly the symptoms that make it harder to diagnose and fix the problem causing them. Food is rationed, but not starvation level. The pre-packaged supplies are designed for caloric sufficiency and nutritional balance, not for pleasure. After a few months, the crew knows every meal in the rotation. The flavors blur together. The textures become monotonous. Small hydroponic gardens can supplement the diet with fresh greens, cherry tomatoes, radishes, but the growing area is small and the yield is limited. Fresh food becomes a psychological event as much as a nutritional one. A handful of salad greens grown under LED lamps on another planet, eaten by people who have not tasted anything genuinely fresh in months. It matters more than the calories suggest. And through all of this, Earth is visible in the Martian sky. Not prominent, not the way the moon dominates Earth's night sky, but visible. A bright bluish point of light near the horizon after sunset or before sunrise. Every person the crew has ever known lives on that point of light. Every place they have ever been. Every sound and smell and sensation they remember from their previous lives. It is right there, visible, and it is roughly 225 million kilometers away on average during the surface day. Close enough to see. Far enough that the light you are looking at left Earth over 12 minutes ago. The home you are staring at is not where it appears to be. It has already moved on. You are looking at a memory projected onto the sky. The psychological weight of this is not speculative. Studies of Antarctic overwintering crews, submarine deployments, and long-duration spaceflight consistently document a phenomenon that researchers call the third quarter effect. Roughly 3/4 of the way through any isolated mission, morale drops measurably. Motivation declines, interpersonal conflicts increase, The end is close enough to anticipate, but not close enough to feel. On a Mars surface stay, the third quarter point falls somewhere around month 11 or 12. The crew has been away from Earth for over a year and a half. The return launch window is still months away. The return journey, another 9 months of confinement, has not even begun. And everything, every piece of equipment, every system, every relationship, every psychological coping mechanism has been under continuous stress for 500 consecutive days with no relief and no escape. This is what it means to stay on Mars. Not to visit, to stay, to live inside a machine on a dead world, breathing recycled air, drinking recycled water, eating the same meals in the same rooms with the same people, watching Earth crawl across a rust-colored sky, waiting for the planets to realign so you can begin the long journey home. Then comes the return journey. Another 9 months of transit. More radiation, more weightlessness, more isolation, more communication delay. This time growing shorter as they approach Earth, but still measured in minutes for most of the trip. But the return journey is not simply a replay of the outbound trip. It is the same crossing made by different people. People who have spent 15 months in Martian gravity, which is roughly 38% of Earth's. Their muscles have weakened despite daily exercise. Their bones have lost density. Their cardiovascular systems have adapted to a lighter workload. Their sense of balance has recalibrated to a world where everything weighs a third of what it should. For 9 months on the way to Mars, their bodies were adjusting to weightlessness or whatever partial gravity the transit vehicle provided. Then, for 15 months on the Martian surface, they adapted again to a gravity field that is neither Earth, normal, nor zero. Now, on the return transit, they face another prolonged period of reduced gravity, pushing their physiological adaptation even further from what Earth demands. And Earth demands a great deal. When the return vehicle reaches Earth and enters the atmosphere, the crew will experience deceleration forces of roughly 4 to 5 times Earth's gravity during the re-entry phase. These are forces that a healthy, Earth-adapted astronaut can tolerate, though not comfortably. But the Mars crew will not be healthy and Earth-adapted. They will have spent nearly 3 years in gravitational environments far below Earth normal. Their bodies will have changed in ways that months of onboard exercise can mitigate, but not eliminate. Bone density will be reduced, muscle mass will be lower, cardiovascular capacity will be diminished, the fluid distribution in their bodies will have shifted. Their inner ear balance systems will have recalibrated to conditions that no longer apply. Re-entry will hit these bodies harder than it would hit an astronaut returning from 6 months on the International Space Station. The station crews who return after half a year in microgravity frequently need assistance standing and walking when they first exit the capsule. Some cannot stand at all without support, and those are astronauts who spent 6 months in reduced gravity, not nearly 3 years. The Mars return crew will be attempting to survive the most physically punishing phase of the entire mission, atmospheric re-entry and landing, in the weakest physical condition of their lives. There is no alternative. You cannot stop the spacecraft and spend a month reconditioning before re-entry. You cannot slow the re-entry to reduce the G-forces without changing the trajectory in ways that create other problems. The crew must endure it as they are. Mission medical planners have studied this extensively, and the consensus is that it is survivable, but with elevated risk. A crew member who has lost Significant bone density could fracture a vertebra under re-entry forces that a fully conditioned person would tolerate without injury. A weakened cardiovascular system could struggle to maintain blood pressure to the brain during sustained high G deceleration, leading to impaired consciousness at the worst possible moment. These are not disqualifying risks. They are managed risks. But they are real, and they are unique to a mission of this duration. The total mission clock, from launch to landing back on Earth, is roughly 900 to 1,000 days, nearly 3 years, and during that entire time, the crew is beyond the reach of any rescue, any resupply, any meaningful real-time assistance from Earth. They are, in every operational sense, alone. This is what the 55 million kilometers a closest approach actually means when you try to cross it. It is not a distance you fly across. It is a system of constraints you navigate through: launch windows, transfer arcs, communication delays, radiation exposure, fuel budgets, landing challenges, surface survival, return timing. Each constraint is shaped by the orbital mechanics of two planets circling the Sun at different speeds. Each one would be challenging on its own. Together they make Mars the most demanding crewed mission ever seriously planned. And Mars sits at 1.52 astronomical units from the Sun. It is the fourth planet, the inner solar system's outermost world, the nearest target beyond our own moon that anyone has ever considered sending humans to. Jupiter is 3.5 times farther out. Saturn is more than 6 times farther. Uranus is more than 12 times farther. Neptune is 20 times farther. Every single constraint that makes Mars difficult, the transit time, the communication delay, the radiation exposure, the fuel requirements, the impossibility of rescue, gets worse as you move outward. Not a little worse, categorically worse. The problems do not add up, they multiply. Because distance in the solar system is not a line you travel along. It is a web of compounding physical realities that wrap tighter around every mission the farther it reaches from the Sun. Mars is hard enough to make seasoned engineers question whether a crewed mission is even advisable within the next few decades. And Mars is the beginning. Beyond it, the solar system opens into gaps so wide and so punishing that the word distance stops being adequate. What waits beyond Mars is not just more space, it is a different kind of problem entirely. One where the sun grows dim, the signals grow faint, and the idea of rescue does not just become unlikely. It becomes meaningless. Everything you just learned about Mars, the launch windows, the curved transfer arcs, the communication delays, the impossibility of rescue, all of it was the easy version. Mars is 1.5 astronomical units from the Sun. It sits just next door in the context of the solar system. A neighbor you can almost reach out and touch if you time it right and carry enough fuel and accept a 9-month journey through the void. What comes next is not a continuation of the same difficulty at a slightly larger scale. It is a change in kind. The gap between Mars and Jupiter is where the solar system stops being merely difficult and starts becoming something closer to hostile by design. But before we reach Jupiter, we have to cross something that most people imagine is a barrier and is actually a demonstration of how empty the solar system truly is. The asteroid belt. You've seen it in movies, a dense field of tumbling boulders, so tightly packed that a spacecraft has to weave and dodge through them like a car through traffic. That image is pure fiction. The real asteroid belt, which occupies a broad ring between roughly 2.2 and 3.3 astronomical units from the Sun, contains millions of objects, but they are spread across such an enormous volume of space that the average distance between any two asteroids is roughly 1,000,000 kilometers or more. That is more than twice the distance from the Earth to the Moon, between each pair of neighboring rocks. Every spacecraft that has ever crossed the asteroid belt, and there have been many, including both Pioneers, both Voyagers, Galileo, Cassini, Juno, and New Horizons, has passed through without incident and without any special evasive maneuvering. The odds of hitting an asteroid during a crossing are estimated at roughly 1 in a billion. The belt is not a wall. It is not even a speed bump. It is a region of slightly higher debris density that is still overwhelmingly, crushingly empty. If you were standing on one of the larger asteroids and looking around, you would not see another asteroid with your naked eye. The nearest one would be a tiny point of reflected light, indistinguishable from a dim star, hundreds of thousands of kilometers away. The asteroid belt matters not because it is dangerous, but because it is instructive. Even in the one region where objects are supposedly crowded together, the distances between them are so vast that a spacecraft sails through without noticing they exist. If the most densely populated zone between Mars and Jupiter is this empty, imagine what the rest of that gap looks like. 3.7 astronomical units of almost nothing. Roughly 550 million kilometers of vacuum, with a scattering of rocks so sparse they might as well not be there. That is the distance a spacecraft must cross just to reach the next planet outward. And it crosses it alone, in silence, for years. On the far side of that emptiness, Jupiter waits. It is not just another planet farther along the line. It is a different category of destination. Jupiter's gravity well is deeper than anything in the inner solar system. Its mass more than twice that of all the other planets combined. Arriving at Jupiter means entering the domain of an object so massive that it distorts the trajectories of everything near it, bends the paths of comets, ejects asteroids, and holds roughly 95 known moons in intricate orbital chains. The orbital insertion burn required to enter Jupiter's orbit demands more precision and more fuel than anything Mars requires because the speeds involved are higher and the penalty for error is absolute. Miss the burn window and the spacecraft sails past Jupiter and out into the void beyond, with no possibility of return. Every mission to Jupiter is a commitment that begins years before arrival and offers no second chance at the critical moment. A Hohmann transfer orbit from Earth to Jupiter takes approximately 2 years and 7 months. That is roughly triple the transit time to Mars. But this number, while technically accurate, understates the reality because almost no mission to Jupiter has ever used a pure Hohmann transfer. The fuel requirements for a direct transfer to Jupiter are so severe that most missions rely on gravity assists, using close flybys of other planets to gain velocity without burning additional propellant. The spacecraft borrows momentum from a planet's orbital motion, stealing a tiny fraction of the planet's energy to fling itself outward faster than its own engines could achieve alone. This concept, the gravity assist, deserves a moment of explanation because it is one of the most counterintuitive and elegant maneuvers in all of spaceflight, and because without it, most of the outer solar system would be permanently out of reach. Here is how it works. A spacecraft approaches a planet on a carefully planned trajectory. As it gets close, the planet's gravity pulls the spacecraft in, accelerating it. The spacecraft swings around the planet in a curved path, gaining speed as it falls toward the planet, and then climbing back out on the other side. If the trajectory is designed correctly, the spacecraft leaves the planet's vicinity traveling faster than it arrived, relative to the Sun. This seems like free energy. It is not. The energy comes from the planet itself. As the spacecraft swings past, it pulls on the planet gravitationally just as the planet pulls on it. The spacecraft gains velocity, and the planet loses an equal amount of momentum. But the planet is so incomprehensibly massive compared to the spacecraft that the change in the planet's motion is unmeasurably small. When Voyager 2 used Jupiter as a gravity assist in 1979, it increased its velocity by roughly 10 kilometers per second. Jupiter, in exchange, slowed down in its orbit by a distance so small it would take the age of the universe to accumulate to a measurable effect. The spacecraft steals speed from a giant too large to notice the theft. The trajectory has to be precise. The angle of approach determines how much velocity is gained and in which direction the spacecraft is flung. Approach too close and the planet's atmosphere or radiation environment can damage or destroy the spacecraft. Approach too far and the gravity assist is too weak to be useful. The sweet spot is a narrow corridor of space around the planet, and hitting it requires course corrections calculated months or years in advance. What makes gravity assist essential for outer solar system missions is simple arithmetic. A spacecraft leaving Earth for Jupiter on a direct Hohmann transfer must carry all the fuel needed to reach Jupiter. That fuel has mass. That mass requires fuel to accelerate. More fuel means more mass, which requires still more fuel. The rocket equation punishes you exponentially for every additional kilometer per second of velocity you want. A gravity assist breaks this cycle by providing velocity without burning fuel. The spacecraft carries less propellant, which makes it lighter, which means the launch vehicle can lift more instruments and equipment, which makes the mission scientifically richer and operationally more capable. Nearly every successful mission to the outer solar system has used at least one gravity assist. Most have used several. It is not a shortcut. The additional planetary flybys add years to the journey. But it is the difference between a mission that can fly and one that cannot. Between a spacecraft that arrives with instruments and data storage and communication capability and one that arrives as little more than an empty fuel tank. The result is written in the flight paths of every mission that has ever reached Jupiter. None of them flew straight there. All of them spent years looping through the inner solar system, collecting speed from planetary flybys before turning outward. The specific routes read like itineraries for a tour of the inner planets that somehow ends at the outer ones. The Galileo spacecraft, launched in October of 1989, did not arrive at Jupiter until December of 1995. That is 6 years of flight. Not because the spacecraft was slow, but because its trajectory included one flyby of Venus and 2 flybys of Earth to gain enough velocity to reach Jupiter with the fuel it could carry. Juno, launched in August of 2011, arrived at Jupiter in July of 2016, approximately 5 years of transit, following a trajectory that included an Earth gravity assist in October of 2013. The spacecraft had already been flying for over 2 years before it swung back past its home planet to pick up the speed it needed to reach Jupiter. And right now, as this is being recorded, NASA's Europa Clipper spacecraft is in the middle of its own long looping journey to Jupiter. It launched in October of 2024. It flew past Mars in early 2025 to pick up a gravity assist. It will swing back past Earth in December of 2026 for another gravity assist, and it will not reach Jupiter until April of 2030. That is 5.5 years from launch to arrival, and the spacecraft will have traveled approximately 2.9 billion kilometers to cover a straight line distance that is a fraction of that. Europa Clipper is one of the most sophisticated planetary science missions ever built, and getting it to Jupiter requires bouncing it around the inner solar system for years like a billiard ball, gradually accumulating the velocity it needs to reach the fifth planet. This is the first thing that changes beyond Mars: time. The transit times are no longer measured in months, they are measured in years. A mission to Jupiter commits everyone involved, the engineers, the scientists, the funding agencies, to a wait measured in the better part of a decade before the first data arrives. If something goes wrong during transit, there is no quick correction. The spacecraft is years away from its destination and months away from any point where a trajectory adjustment could help. The margins are thinner, the distance is larger, and every error has longer to compound before anyone can detect it or respond. Now consider communication. At Jupiter's average distance from Earth, a one-way radio signal takes between 33 and 54 minutes, depending on where both planets are in their orbits. A round trip, sending a command and receiving confirmation, takes over an hour at the closest and nearly 2 hours at the farthest. Think about what that means for mission operations. When Juno performs a close flyby of Jupiter, skimming through the upper atmosphere to study its structure and magnetic field, the maneuver is over before ground controllers know it has begun. Every orbital insertion, every instrument deployment, every critical engine burn must be pre-programmed and executed autonomously by the spacecraft. The ground team watches the telemetry afterward, reading data that describes events that happened nearly an hour ago. For a robotic mission, this is manageable through careful planning and reliable software. For a hypothetical human mission to the Jupiter system, it would mean something far more unsettling. A crew near Jupiter would experience communication with Earth as a series of monologues, separated by hour-long silences. You send a message, you wait more. Eventually a response arrives, answering a question you asked over an hour ago, referencing a situation that may have already changed. Conversation in any normal sense is gone. What remains is correspondence, slow and asynchronous, like exchanging letters across an ocean in the 18th century. Except the ocean is made of vacuum and radiation. And speaking of radiation, Jupiter presents a hazard that exists nowhere else in the solar system at this intensity. Jupiter has the strongest magnetic field of any planet, roughly 20,000 times more powerful than Earth's. This magnetic field traps and accelerates charged particles, mostly electrons and protons stripped from the solar wind and from the volcanic eruptions of its moon, Io, creating radiation belts so intense they can destroy unshielded electronics within days and deliver lethal doses to biological tissue within hours. The radiation environment near Jupiter is not a theoretical concern whispered about in planning documents. It is the defining engineering constraint of every mission that has ever operated there. When the Galileo spacecraft entered orbit around Jupiter in 1995, its instruments suffered from radiation-induced noise and degradation throughout the mission. Certain detectors saturated, data became corrupted. Systems that were designed to withstand the radiation environment performed at the edge of their tolerances. Galileo lasted 8 years in the Jupiter system, far beyond its original design life, but the radiation exacted a heavy toll on its hardware throughout. Juno, which has been orbiting Jupiter since 2016, was designed with the radiation problem as a central constraint. Its most sensitive electronics are housed inside a titanium vault, a shielded container roughly the size of an automobile trunk, with walls about a centimeter thick, specifically built to protect the spacecraft's brain from Jupiter's radiation belts. Juno's orbit was deliberately shaped to minimize time spent in the most intense radiation zones. It follows a long elliptical path that carries it far out from Jupiter for most of each orbit, and then dives quickly through the inner radiation belts during its closest approaches. Even with this strategy, Juno accumulates radiation dose with every pass. The mission was designed for a limited number of close approaches precisely because each one degrades the electronics a little further. Europa Clipper, currently en route, takes the same philosophy even further. Instead of orbiting Europa directly, which would expose the spacecraft to constant bombardment from Jupiter's radiation belts, it will orbit Jupiter on a wide, looping path and conduct 49 targeted flybys of Europa over its 4-year primary mission. Each flyby brings the spacecraft into the intense radiation zone for a brief period, then carries it back out to recover. The entire mission architecture is shaped around survival in a radiation field that would fry an unshielded spacecraft in a matter of days. The European Space Agency has stated plainly that a human astronaut standing on the surface of Europa, which orbits deep within Jupiter's radiation belts, would receive a lethal radiation dose within a matter of hours. Not over months or years, hours. Jupiter's inner moons exist inside a particle accelerator the size of a small solar system. This is not an environment where current or foreseeable human spaceflight technology can operate safely for extended periods. It is an environment where even our most radiation-hardened robotic spacecraft must be designed from the ground up to survive, and then strategically flown to minimize exposure. Jupiter is hostile not only around it, but within it. Months before the Galileo spacecraft arrived at Jupiter, it released a small atmospheric probe on a collision course with the planet. On December 7th, 1995, the same day Galileo entered orbit, that probe struck Jupiter's cloud tops. The probe hit Jupiter's upper atmosphere at roughly 47 kilometers per second, experiencing deceleration forces of roughly 230 times Earth's gravity, the most extreme atmospheric entry ever survived by a human-built object. The heat shield held, the parachute deployed, and for the next 57 minutes, the probe descended into an environment of increasing pressure and temperature, transmitting data on wind speed, chemical composition, cloud structure, and atmospheric density back to the Galileo orbiter above. At a depth of roughly 150 kilometers below the cloud tops, the signal went silent. The temperature had reached approximately 153 degrees Celsius. The pressure had climbed to roughly 23 times Earth's atmospheric pressure at sea level. The probe was crushed, then melted, then vaporized, absorbed into an atmosphere so massive and so violent that the entire Earth could be swallowed in it without producing a visible ripple. 57 minutes of survival inside the largest planet in the solar system. That is what Jupiter does to harden titanium and aerospace engineering. Now add the power problem. Every spacecraft needs energy to operate. Instruments need power to collect data. Communication systems need power to transmit that data back to Earth. Computers need power to process commands. Heaters need power to keep electronics from freezing in the cold of deep space. On Earth and in near-Earth space, solar panels work beautifully. At Earth distance from the Sun, roughly 1,360 watts of solar energy fall on every square meter of surface. That is abundant, reliable, and free. But solar energy obeys the inverse square law. Double your distance from the Sun, and the intensity drops to 1/4. Triple your distance, and it drops to 1/9. At Jupiter's distance, 5.2 times farther from the Sun than Earth, the solar energy available is roughly 1/27th of what Earth receives. That is approximately 50 watts per square meter, down from 1,360. At Earth, a modest solar panel can power a household. At Jupiter, the same panel would struggle to power a desk lamp. This is why every Jupiter mission before Juno relied on nuclear power rather than solar. The Pioneer missions, both Voyagers and Galileo, all carried radioisotope thermoelectric generators, devices that convert the heat from decaying plutonium into electricity. These generators are reliable, long-lived, and produce power regardless of distance from the Sun. They are also heavy, expensive, politically sensitive because they contain plutonium and limited in the amount of power they produce. A typical radioisotope thermoelectric generator provides a few hundred watts at the start of a mission, declining gradually as the plutonium decays. That is enough for a robotic spacecraft with carefully designed low-power instruments, but it is a tiny fraction of what a crewed vessel would need for life support, lighting, heating, and communications. Juno was the first spacecraft to use solar panels at Jupiter, but only because its panels are enormous, with 3 wings covering a total area of roughly 72 square meters, and because the mission's power requirements were specifically designed to be achievable within the constraints of Jupiter-distant solar energy. Even so, Juno generates only about 450 watts at Jupiter, roughly enough to power 4 or 5 household light bulbs. The spacecraft's instruments, computers, and communication systems all operate within this tight power budget. Any human presence at Jupiter would require orders of magnitude more power, and neither solar panels nor current nuclear generators can provide it at this distance without becoming impractically large or heavy. Saturn makes everything worse. It orbits at approximately 9.58 astronomical units from the Sun, nearly twice as far as Jupiter. A minimum energy Hohmann transfer from Earth to Saturn takes roughly 6 years. The Cassini spacecraft, one of the most successful planetary missions ever flown, launched in October of 1997 and did not arrive at Saturn until July of 2004. Nearly 7 years of transit, including gravity assist from Venus twice, Earth once, and Jupiter once. The spacecraft looped through the inner solar system for years, gaining speed with each flyby before it had enough momentum to reach Saturn. 7 years. From launch to arrival, nearly a full decade passed if you include the years of final design and assembly before launch. The scientists who proposed Cassini in the 1980s did not see their first Saturn data until 17 years later. An entire generation of graduate students grew up, completed their degrees, and moved on before the mission they were trained for delivered its first results. That is the timescale of outer solar system exploration. Not months, not years, but decades of sustained commitment before a single image arrives. Cassini did not travel to Saturn alone. Bolted to its underside was a small probe called Huygens, built by the European Space Agency, designed for a one-way trip to the surface of Titan, Saturn's largest moon. Titan is the only moon in the solar system with a dense atmosphere, a thick orange haze of nitrogen and methane that completely obscures its surface from orbit. Nobody knew what lay beneath those clouds. Radar and infrared instruments had offered hints, suggestions of lakes, channels, maybe even rain, but no one had ever seen the surface directly. Huygens was built to find out. On January 14th, 2005, after 7 years of riding on Cassini's back across the solar system, Huygens separated and began its descent into Titan's atmosphere. The probe hit the top of the atmosphere at roughly 6 kilometers per second and began decelerating. A heat shield absorbed the initial friction. Then a series of parachutes deployed, slowing the probe further as it drifted down through the haze. The descent took approximately 2 hours and 27 minutes. During that time, Huygens transmitted data back to Cassini, which relayed it to Earth. The relay was the only option. Huygens had no antenna powerful enough to communicate directly with Earth from the surface of Titan. Its signal had to go up to Cassini in orbit and then be retransmitted across the gap to Earth. And that retransmission took time. The data that Huygens collected during its descent and brief surface stay had to travel from Titan to Cassini, roughly a few thousand kilometers, and then from Cassini to Earth, roughly 1.2 billion kilometers. The light travel time from Saturn to Earth on that day was approximately 67 minutes. Mission controllers received the first images from Titan's surface more than an hour after they were taken. What those images showed was extraordinary. A frozen landscape of water ice, stained dark by organic compounds, with rounded pebbles scattered across a flat plain. The pebbles appeared to have been shaped by flowing liquid, the same way river rocks are rounded on Earth. Channels carved into the terrain above the landing site looked like drainage networks. Valleys cut by liquid methane rain flowing downhill and pooling in low areas. Titan had weather. It had rain. It had rivers and lakes, not of water, but of liquid methane and ethane, cycling through a hydrological system that mirrored Earth's in structure while being utterly alien in chemistry. Huygens survived on the surface for approximately 72 minutes before its batteries died and the signal went silent. In that brief window, it returned data from the most distant surface landing ever achieved by a human-built object. A small probe, on a frozen plain, on a moon orbiting a planet nearly 10 astronomical units from the sun, sending back images of a world no human eye had ever seen. Images that took over an hour to reach the people waiting to see them. That landing happened because the Cassini-Huygens mission had been conceived in the early 1980s, funded through the late 80s and 90s, launched in 1997, and flown for 7 years before Huygens got its single chance. 25 years from first concept to surface data. A quarter of a century of sustained effort to land a probe for 72 minutes on a world so far away that the scientists could not even see their own data arriving in real time. That is what Saturn distance exploration demands, not just engineering. Patience measured in generations. Communication delay at Saturn ranges from approximately 68 minutes to 95 minutes each way. A round-trip exchange takes more than 2 hours at the closest and over 3 hours at the farthest. When Cassini performed its final plunge into Saturn's atmosphere in September of 2017, the signal confirming the spacecraft's destruction took 83 minutes to reach Earth. The scientists and engineers who had guided Cassini for 20 years watched the telemetry go flat and knew that what they were seeing had already happened an hour and 23 minutes ago. The spacecraft had already burned up. The mission was already over. They were mourning something that had ended before they even knew it was gone. Solar power at Saturn is essentially non-existent for practical purposes. At nearly 10 astronomical units from the Sun, the solar energy is roughly 1% of what Earth receives. Approximately 15 watts per square meter. No currently feasible solar panel array could power a meaningful spacecraft at this distance. Every mission to Saturn has relied on nuclear power, and every future mission will too, unless revolutionary advances in power generation emerge. This means that the supply of plutonium-238, the specific isotope used in spacecraft radioisotope generators, becomes a limiting factor in outer solar system exploration. The United States restarted production of plutonium-238 after a long hiatus, but output is measured in kilograms per year, and each mission consumes a significant fraction of the available supply. There is no alternative supplier. There is no synthetic substitute. Every future outer solar system mission competes for the same small annual output of the same single isotope, produced at a single facility, funded by a single government. The distance to the outer planets is not just a physics problem. It is a supply chain problem, a materials problem, a political funding problem, all layered on top of the orbital mechanics. Saturn also introduces a subtler challenge that compounds everything else: the sheer longevity required of the hardware. A spacecraft that takes 7 years to reach Saturn and then operates for 13 years in orbit, as Cassini did, must function reliably for 2 decades in the most hostile environment imaginable. Vacuum, extreme temperature swings, radiation, micrometeorite impacts, and the gradual degradation of every material, lubricant, seal, and circuit aboard. Every component has to be designed not just to work, but to keep working for longer than many engineers' entire careers. The reaction wheels that keep the spacecraft pointed at its target must spin without failure for 20 years. The radio transmitter that sends data back to Earth must maintain frequency stability across 2 decades of thermal cycling. The software must handle situations that nobody anticipated during development, because 20 years is long enough for the unexpected to become the inevitable. The Voyager spacecraft illustrate this longevity challenge and its limits. Voyager 1 and Voyager 2, both launched in 1977, flew past Jupiter and Saturn in the late 1970s and early 1980s. Voyager 2 continued to Uranus in 1986 and Neptune in 1989. Both spacecraft are still transmitting data nearly 5 decades after launch, operating on radioisotope generators that now produce less than half of their original power output. Instrument after instrument has been shut down to conserve energy. The heaters that keep fuel lines from freezing have been turned off. The power budget is managed down to individual watts. These spacecraft were built to last 5 years. They have lasted nearly 50, a testament to extraordinary engineering, but also a demonstration of what deep space does to machines over time. Every system is degraded. Every component is older than it was designed to be. The spacecraft survive, but they survive diminished, running on the fading heat of decaying plutonium, sending whispers across billions of kilometers to antenna dishes that must strain to hear them. And this degradation is not unique to aging Voyager hardware. It is the inevitable consequence of operating any machine at these distances for these durations. The farther you go, the longer the journey takes. The longer the journey takes, the more time every system has to wear down, drift out of calibration, or fail. And the farther you are from Earth, the less anyone can do about it. At Jupiter, a failure might be diagnosed within an hour and a corrective command sent within 2. At Saturn, the same process takes 3 or 4 hours. The lag is not merely inconvenient. It means that a cascading failure, one system breaking and putting stress on another, can propagate through the spacecraft for hours before ground controllers even know it has started. There is one more dimension of the Jupiter and Saturn problem that deserves attention, and it is the one that rarely makes it into popular discussions of planetary exploration. It is the question of what you're giving up by going there. Every spacecraft sent to Jupiter or Saturn represents years of design, billions of dollars in funding, and a substantial fraction of a space agency's institutional capacity. The Cassini mission, from initial concept to end of operations, spanned roughly 30 years of effort and cost, approximately $3.9 billion in total. Europa Clipper carries an estimated $5 billion price tag. These are not line items in a budget. They are generational investments, absorbing the careers of hundreds of engineers and scientists, occupying clean rooms and launch pads, and deep space network antenna time that could otherwise be used for other missions. And because the journeys take so long, the feedback cycle is agonizingly slow. If a mission to Saturn reveals something unexpected, something that demands a follow-up investigation, the earliest a follow-up spacecraft could arrive is roughly a decade later, assuming one were funded and built immediately after the discovery. In practice, the gap between missions to any single outer planet has been measured in decades. Cassini arrived at Saturn 23 years after Voyager 2 flew past. No spacecraft has returned to Uranus since Voyager 2's flyby in 1986, 40 years ago. No spacecraft has returned to Neptune since Voyager 2's flyby in 1989. The distances are so great and the missions so expensive that the outer solar system is explored in single visits, separated by entire human generations. This is the widening trap. It is not just that Jupiter and Saturn are far. It is that their distance cascades into every other variable that determines whether a mission is possible and whether it succeeds. Transit times measured in years, communication delays measured in hours, power budgets so thin that every watt is rationed, radiation so intense it reshapes mission architecture from the ground up, hardware that must last decades without maintenance, costs that consume billions, and careers that are measured against the timeline of a single mission. Each variable feeds the others. Longer distances mean longer transits. Longer transits mean more wear on hardware. More wear means more redundancy, which means more mass, which means more fuel, which means a heavier spacecraft, which means a more expensive launch, which means a longer wait for funding. The trap tightens with every step outward, and Jupiter and Saturn are not the edge of the solar system. They are the middle. Beyond Saturn, the distances do not merely grow, they yawn open. 2 more planets wait out there in the dark, so far from the sun that sunlight at their surfaces is barely distinguishable from the starlight. They have been visited exactly once each, by a single spacecraft riding us planetary alignment that will not repeat for another century and a half. They are the least explored, least understood major worlds in our solar system, and the reasons for that are about to become painfully clear. Beyond Saturn, the solar system enters a kind of silence. Not literal silence, because space is always silent, but a silence of human presence. A silence of data. A silence of knowledge. Jupiter has been orbited by multiple spacecraft. Saturn was studied for 13 years by Cassini. But Uranus and Neptune, the two outermost major planets, have each been visited exactly once by the same spacecraft during a window of opportunity that opened for a few years in the late 1980s and will not open again until the middle of the 22nd century. Voyager 2 flew past Uranus on January 24th, 1986. It flew past Neptune on August 25th, 1989. Those two encounters, each lasting only a few hours of close observation, represent the entirety of humanity's direct exploration of the ice giants. Everything we know about Uranus and Neptune beyond what ground-based and space-based telescopes can observe from billions of kilometers away comes from a single spacecraft that passed through each system nearly 4 decades ago. 2 of the 8 major planets in our solar system have been studied up close for a combined total of less than 1 day, and yet even those brief hours of observation transformed our understanding of both worlds. At Uranus, Voyager 2 discovered 10 previously unknown moons in a single flyby, bringing the total at the time to 15. It revealed that Uranus's magnetic field is tilted at a steep angle relative to its rotational axis, nearly 60 degrees, nothing like the roughly aligned magnetic fields of Earth, Jupiter, or Saturn. This bizarre tilt suggested that Uranus's interior structure is fundamentally different from the other giant planets, but with only a few hours of close data, the reason remained unknown. Voyager 2 also captured images of Miranda, the innermost of Uranus's large moons, revealing a surface so fractured and jumbled that it looked as though the moon had been shattered and reassembled. Enormous cliffs, some of the tallest in the solar system, dropped roughly 20 kilometers from ridgeline to valley floor. Whatever happened to Miranda, it was violent. And with one flyby's worth of data, we still do not know what it was. At Neptune, the surprises were even more dramatic. Voyager 2 discovered that despite being the farthest major planet from the Sun, receiving almost no solar heat, Neptune has the fastest sustained winds ever measured on any planet. Wind speeds exceeding 2,000 kilometers per hour, driven by an internal heat source that radiates more than twice as much energy as Neptune receives from the Sun. The spacecraft also captured the first close images of Triton, Neptune's largest moon, and found a world covered in nitrogen ice with active geysers shooting plumes of dark material 8 kilometers into the thin atmosphere. Triton orbits Neptune in the opposite direction from the planet's rotation, a strong indicator that it was captured from the Kuiper belt rather than forming alongside Neptune. It may have a subsurface ocean. It is one of the most geologically interesting objects in the solar system, and everything we know about it comes from a single afternoon of observation in August of 1989. Those discoveries did not close questions. They opened them. Every answer Voyager 2 brought back from the ice giants generated dozens of new puzzles that cannot be resolved without going back. And going back is the problem, because the distances that made those flybys so brief are the same distances that have kept every space agency on Earth from returning for nearly 4 decades. The reason for this is not lack of interest. Planetary scientists have been advocating for dedicated missions to the ice giants for decades. Uranus and Neptune are scientifically extraordinary. They are a class of planet ice giants that appears to be among the most common types in the galaxy based on exoplanet surveys. Understanding them is essential to understanding planetary formation itself. Their tilted magnetic fields bizarre internal structures, complex moon systems, and faint ring systems are full of unanswered questions. The scientific case for returning to these worlds is overwhelming. The reason we have not gone back is distance. Pure, punishing, mission-breaking distance. Uranus orbits the Sun at approximately 19.14 astronomical units. That is roughly 4 times farther from the Sun than Jupiter, and twice as far as Saturn. A minimum energy Hohmann transfer from Earth to Uranus would take approximately 16 years. 16 years of coasting through the void before a single observation can be made. No spacecraft has ever attempted this direct route because the transit time alone is longer than most mission budgets can sustain. Engineers retire. Funding cycles turn over. Institutional knowledge erodes. A 16-year cruise phase means the people who arrive at mission operations to guide the spacecraft into orbit may not be the same people who designed it. The only practical way to shorten the journey is with gravity assists, and even those only compress the timeline so much. The proposed Uranus orbiter and probe, currently ranked as the highest priority flagship mission in planetary science by the most recent decadal survey, would use a Jupiter gravity assist to reach Uranus in approximately 12 to 14 years. That is the fastest realistic option with current or near-term propulsion technology. 12 to 14 years of flight. A spacecraft launched in the early 2030s would not arrive at Uranus until the mid-2040s at the earliest. Scientists proposing this mission today are planning for data that their graduate students may be the ones to analyze. And this timeline is already slipping. NASA has acknowledged that a shortfall in the production of plutonium-238, the isotope that powers radioisotope thermoelectric generators for deep space missions, has pushed the likely launch window from the early 2030s to the mid to late 2030s. A later launch means missing the optimal Jupiter gravity assist window, which in turn could add years to the transit time or require a less favorable trajectory. The distance to Uranus does not just constrain the mission design. It propagates backward through the entire planning process, turning supply chain problems and budget shortfalls into years of additional delay before a spacecraft even leaves Earth. Communication at Uranus is another step beyond what Jupiter and Saturn demand. At Uranus's distance, a one-way radio signal takes approximately 2.5 to 3 hours to travel between the spacecraft and Earth. A round-trip exchange takes 5 to 6 hours. If a spacecraft at Uranus encounters a problem and sends an alert to Earth, the ground team receives the alert 3 hours after it was sent. They analyze the situation, formulate a response, and transmit it. Another 3 hours pass before the spacecraft receives the command. 6 hours from the moment the problem began to the moment the spacecraft gets its first instruction from Earth. In 6 hours, a malfunctioning thruster can send a spacecraft tumbling. A software glitch can corrupt a data recorder. A stuck valve can drain a propellant tank. The spacecraft must be designed to handle any plausible emergency entirely on its own for at least 6 hours, and more realistically for much longer, because a single command response cycle rarely solves a complex problem. Solar power at Uranus is functionally non-existent. At 19 astronomical units from the Sun, the solar energy available is roughly 1/366th of what Earth receives, approximately 3.7 watts per square meter. To put that in perspective, A standard household light bulb draws about 60 watts. You would need over 16 square meters of perfectly efficient solar panels at Uranus to power a single light bulb. Real solar panels are not perfectly efficient. At current conversion rates, you would need many times the area. No solar-powered mission to Uranus is feasible with existing technology. Every proposed Uranus mission relies on nuclear power, and the plutonium supply constraints make even that challenging. Voyager 2 reached Uranus after 8.5 years of flight, but only because it rode the most favorable planetary alignment in 175 years. Jupiter, Saturn, Uranus, and Neptune were all arranged on the same side of the Sun in a configuration that allowed a single spacecraft to use gravity assist from each planet in sequence, picking up speed at every encounter. Without that alignment, Voyager 2 could never have reached Uranus and Neptune on any reasonable timescale. That alignment began to close in the early 1990s, and a similar configuration will not occur again until the 22nd century. We cannot replicate Voyager 2's Grand Tour. We can only plan single target missions that take a decade or more to arrive. Neptune is the end of the line. It orbits at roughly 30.2 astronomical units from the Sun, more than 30 times farther from the Sun than Earth is. A Hohmann transfer from Earth to Neptune would take approximately 30 years. 30 years of flight. A spacecraft launched when a mission scientist is 35 years old would arrive when that scientist is 65. The entire productive career of a researcher consumed by the transit phase of a single mission. Voyager 2 reached Neptune in 12 years, but again, only because of the extraordinary planetary alignment and the accumulated velocity from 3 prior gravity assists. No dedicated Neptune orbiter has ever been built, funded, or launched. The Neptune Odyssey mission concept, studied by planetary scientists, envisions an orbiter that would take roughly 12 to 16 years to reach Neptune with a Jupiter gravity assist. The estimated cost runs into the billions. No space agency has committed to building it. Communication delay at Neptune reaches approximately 4 to 4.5 hours each way. A round-trip exchange takes 8 to 9 hours. A full working day on Earth could pass between sending a command and receiving confirmation that it was executed. The spacecraft would essentially operate as an autonomous robot for every practical purpose, with Earth providing only high-level guidance on timescales, measured in days rather than minutes or hours. Sunlight at Neptune is approximately 1.5 watts per square meter. 1.5 watts spread across an entire square meter of space. At Earth, you receive roughly 1,360 watts on that same area. Neptune receives approximately 1/900th of the solar energy that Earth does. The Sun, from Neptune's distance, is still the brightest object in the sky, but it is no longer a disk. It is a brilliant point of light, roughly 450 times brighter than the full moon as seen from Earth, but small enough that you could cover it with a pinhead held at arm's length. It provides enough light to see by, barely, but virtually no usable energy. Any spacecraft at Neptune is powered by nuclear decay and nothing else. And yet Neptune is not the edge of the solar system. Beyond Neptune lies the Kuiper Belt, a vast region of icy bodies stretching from roughly 30 to 50 astronomical units, and beyond that, the scattered disk and ultimately the Oort cloud. a spherical shell of comets that may extend halfway to the nearest star. The solar system does not end at Neptune. It fades gradually across distances so enormous that the planets themselves become footnotes in the geography of the Sun's gravitational domain. But for the purposes of what we have been building toward tonight, Neptune is far enough. Because by the time you reach Neptune, every single problem that made Mars difficult has been amplified to the point where the word difficult no longer fits. Transit times of a decade or more, communication delays measured in hours, solar power reduced to a faint whisper, nuclear fuel supplies constrained by global production bottlenecks, hardware that must function autonomously for longer than many human careers. Rescue not just impossible but conceptually absurd, like discussing emergency plumbing on a ship in the middle of the Pacific in the 17th century. There is no one to call. There is nowhere to go. There is only the spacecraft, the void, and the mathematics. This is the moment to step back and look at the whole picture. Not planet by planet, but all at once. The solar system, the one you grew up with, the one on the classroom wall, is a fiction. Not in the sense that the planets are not real. They are real. They are there. Mercury bakes in the sun's glare. Venus chokes under its greenhouse sky. Mars rusts in its thin, cold atmosphere. Jupiter churns with storms older than human civilization. Saturn floats inside its impossible rings. Uranus rolls sideways through the dark. Neptune howls with the fastest winds in the solar system. They are all real, all extraordinary, all worthy of the names and stories we have given them. But the picture that puts them side by side, close enough to compare, close enough to visit in sequence, that picture erases the thing that defines the solar system more than any planet does. The space between them, the gaps, the silence, the emptiness that is not empty at all but filled with physics, with constraints, with time, with danger. When you look at the real solar system, scaled honestly, what you see is mostly nothing. Vast reaches of vacuum punctuated by tiny specks at widening intervals. The inner four planets are huddled close to the sun, all within a region so small that it would be a single dot on a map that also showed Neptune. Then a wide gap to Jupiter, then a wider gap to Saturn, then a gap nearly as wide as everything that came before it to Uranus, then another enormous gap to Neptune. Each step outward is not just longer than the last, it is longer than everything before it combined. The solar system is not a chain of worlds. It is a series of expanding voids, with specks of matter scattered through them at growing distances. And those specks are not standing still. They are all moving, all orbiting at their own pace, all shifting their positions relative to each other every second of every day. The distance between any two planets is never the same twice. It oscillates, swings, stretches, and contracts on cycles that range from months to centuries. The solar system is not a map. It is a clock, a machine of interlocking orbits, each gear turning at its own rate, each gap opening and closing on its own schedule. This means that planetary travel is never a solved problem. You do not figure out how to get to Mars once and then repeat the same journey whenever you like. Each launch window presents a slightly different geometry, a slightly different transfer arc, a slightly different fuel budget. Each mission to Jupiter must account for where Jupiter actually is in its 12-year orbit, and where the gravity assist planets are in theirs. Each proposed mission to Uranus or Neptune must be designed around a specific planetary alignment that may not repeat for decades. The solar system does not sit still and let you plan at your leisure. It moves, and you must move with it, or wait. And the moving is the easy part. The hard part is what happens during the crossing. The communication delays that cut you off from real-time contact with Earth. The radiation that damages electronics and DNA. The solar power that drains away to nothing as you leave the inner solar system behind. The fuel constraints that dictate your trajectory and leave no room for error. The years, sometimes decades, that pass between launch and arrival, during which hardware ages, funding cycles turn, scientific priorities shift, and the people who design the mission retire or pass away before it delivers its first result. Each of these constraints is manageable on its own for any single planet. We can build radiation-hardened electronics, we can design nuclear power systems, we can develop autonomous software, we can plan long missions and sustain institutional commitment across decades. We have done all of these things. The Voyager missions proved it was possible nearly 50 years ago. Cassini proved it again. Juno and Europa Clipper are proving it now. But the constraints multiply as you move outward. They do not simply add to each other, they interact, amplifying each other in ways that make every step beyond Mars dramatically harder than the one before. Longer distances mean longer transit times. Longer transits mean more hardware degradation. More degradation means more redundancy. More redundancy means more mass. More mass means more fuel. More fuel means a larger launch vehicle. A larger launch vehicle means more cost. More cost means more time spent in the funding process before the mission even begins. And by the time the mission finally launches, the planetary alignment may have shifted, requiring a different trajectory, different fuel budget, different arrival date. The entire calculation starts over. This is why the outer solar system remains almost unexplored. Not because we lack curiosity, not because we lack capability, but because the distances impose a compounding tax on every aspect of mission design that grows steeper with every astronomical unit outward from the Sun. The solar system is not withholding its secrets out of malice. It is simply large, unimaginably, operationally, structurally large. And that largeness is not a uniform emptiness you can power through with enough thrust. It is a gradient of increasing difficulty that turns each next planet from a destination into a commitment measured in decades, billions of dollars, and the working lifetimes of the people who attempt it. The planets are familiar because we can name them. We learned them as children, recited them in order, colored them in worksheets, hung them from coat hangers in papier-mâché models. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, 8 names, 8 worlds. They feel close because they're close in our language, in our culture, in the tidy diagrams that line them up side by side like neighbors on a street. But reaching them is another matter entirely. Mars, the nearest and easiest, demands launch windows every 26 months, 9 months of flight, a communication delay that makes real-time control impossible, and a commitment to self-sufficiency that no crewed mission has ever attempted. Jupiter demands years of travel, hours of communication lag, radiation belts that reshape mission architecture from the ground up, and power systems that cannot rely on the Sun. Saturn demands nearly a decade of transit, communication measured in hours, and nuclear fuel whose global supply is measured in kilograms per year. Uranus demands 12 to 14 years of patience and hardware that must outlast the careers of the people who built it. Neptune demands everything Uranus demands and more, stretched to the breaking point of institutional memory and engineering endurance. Each planet is harder to reach than the one before. Not a little harder, fundamentally harder. Each gap between them is wider than the last. Each crossing takes longer, costs more, demands more from the hardware, and isolates the spacecraft further from any possibility of help. The solar system does not become gradually more challenging as you move outward. It becomes exponentially more challenging, each step outward multiplying the constraints that were already severe at the step before. And the most unsettling realization is this: we are not talking about exotic faraway corners of the cosmos. We are talking about our own solar system, our own neighborhood, the 8 planets that orbit our own star, the places we can see with backyard telescopes on a clear night. If the distances between these familiar, named, well-studied worlds are already this punishing, then the void between our solar system and the nearest star, over 260,000 astronomical units away, is not just far. It is a different universe of difficulty. The space between the planets is where we learn how fragile exploration becomes. The space between the stars is where we would learn whether it is possible at all. But that is a question for another night. Tonight, the lesson is closer to home. The solar system is not what the diagram told you it was. It is not a row of planets sitting neatly beside a star, waiting to be visited in sequence. It is not a road with stops along the way. It is not a map, where the distance between 2 points is a fixed number you can look up and plan around. The solar system is a moving system, a machine of orbits and timing, of curved paths and changing gaps, of windows that open briefly and close for years. The planets are not destinations in the way that cities are destinations. They are moving targets on elliptical tracks, each one farther and harder to reach than the last, each one surrounded by widening zones of communication delay, power loss, radiation exposure, and total isolation from help. The spaces between the planets are not empty pauses between interesting places. They are the defining feature of the solar system. They are where the physics lives, where the constraints accumulate, where every mission becomes a negotiation between what we want to know and what the universe will let us attempt. The planets themselves are tiny islands in an ocean of difficulty, and the ocean grows wider and deeper with every step outward from the sun. Tonight, we have traveled from the classroom wall to the orbit of Neptune. We have watched the distances grow, the delays lengthen, the power fade, and the margins shrink. We have seen that the solar system is not a collection of worlds conveniently arranged for our exploration. It is a vast, dynamic, unforgiving arrangement of distance, motion, timing, and danger draped around a single ordinary star. The planets are real. They are magnificent. They are worth every effort we have made and will make to reach them. But the distances between them are the true measure of what we are up against. And those distances are far worse than most people ever imagine, because they are not just numbers on a chart. They are years of your life. They are hours of silence. They are watts of power you no longer have. They are the impossibility of rescue, the degradation of hardware, the fading of the sun behind you as you push outward into a system that grows darker and lonelier with every passing astronomical unit. That is the solar system, not the diagram, not the poster, not the model, the real one, the one that moves, the one that waits, the one that does not care how badly you want to cross it. And it starts just next door with Mars, a planet close enough to see with your naked eye on a clear night, close enough to feel familiar, and already hard enough to humble every engineer who has ever tried to get there. Good night.